Well, good morning, good afternoon, or good evening, depending on your time zone, latitude, and approximation of pi. And hello from your friendly secular astronomer. And great to be with you today to discuss math and calculation and history and all kinds of fun stuff, plus other J-random things that we come up with. Allegedly. Do we have to do this again? Am I muted too? Is that, I guess that's the question. Are you muted? Are we both muted? Or is the stream muted? Maybe we should start again. I hope folks are going to do the right thing and to subscribe, hit the like button, all that good stuff that helps the algorithm, because he's gone past his paper 1,000 digit in the background. He says he's working on a wooden 10,000 digit celebration for his 10,000 subscriber. I think perhaps when you reach 100,000, you should be forced to go on to a show and recite all 100,000 digits of pi.
Oh, jeez, that would be... I can barely recite 10 digits of pi, let alone 100 digit, or let alone 100,000 digits. But
and getting the digits is easy.
Yeah, but I just
getting those digits there, you just read them off, right? And by the way, I am hearing myself.
Okay, well, I just want to, whilst we, what I want to do is I want to just...
So if you recited...
What's that? Oh, I thought you were about to say something, but...
Hearing myself after about a 5-second delay?
It might be... That might just be...
Test. Let's see. I think we're fine. All right, maybe we're fine. Okay. Okay. So as I say, if you recited 100,000 digits, 1 per second, 3.141159, then it would take you 27 hours to do 100,000 digits. Now you could build a sound file where you speak at maybe 2 digits per second. That would be and have a stream going on in the live background. So why don't you do that? Would be, I think, for your 100,000 subscribers. If you did it 2 per second, that would take you a little under 14 hours. You could have that with your voice computer generated in the background, going through in a stream going on the side while you have your celebration of your 100,000 subscribers.
That would actually be something that would be very interesting to do.
I don't hear you.
Oh, what?
If you're speaking.
Wait, what? That's... I think...
I am not hearing you. Why am I not hearing you?
Okay, that's...
Let me make sure. Let me make sure that this is going in the right way. Here's the settings, video.
What I'll do is, whilst you're doing that, I will, I'll shell out my membership. So with the memberships, I have now got the new Flat Earth emoji, and there. Some people may say that Australia is missing.
Not hearing.
And I mean, Flat Earth, Australia just doesn't exist on Flat Earth, so that's why. So I'll just put that in the chat there, and yeah. So you get access to a new emoji,
I'm
and
going to go back into the user settings. And go back into voice and video.
and
Test.
yeah, I can hear you. Well,
I'm now hearing you. We have restored sound. Thank you very much.
Okay. There we go. Yeah, I was just chilling out my memberships there for a second. Once we get to 15 members, we get a new emoji, and someone had a good idea recently of like having a penguin with an AK-47 emoji, or a penguin with a gun.
Yeah.
So,
well, like I said, so you build that sound file of your voice digits 2 per second, or you could lower to a second. You could do a 12-hour stream, have that sound in the background with a running thing on the front, and celebrate your 100,000. But people have to subscribe to push you to the stage where you get to 100,000.
Yeah, and then I actually get one of the proper YouTube things that I'll be able to put there.
Yes.
But that actually, I'll have to keep that in mind, because that actually sounds better than doing a 100-hour stream, so...
Yeah, and again, it could just be as part of your sub thing in the background of you reciting things and going on the thing, while you have a hangout with your friends in this sort of pie drawing in the background.
Mm.
And, get to the 6 nines of pi and all kinds of good stuff. So.
Yeah. Anyway, so let's start with... I think a good place to start would be with ways to calculate pi and ways to... So obviously there's... What you can do is you can measure pi, or measure an approximation of pi using... I mean, tape measure would kind of work, or you could... Depending on whatever it is that you want to use to calculate it, I guess. So, how much precision have we gotten through physically measuring it? Do you know?
That's actually a great question. And looking because pi is a constant, mathematical constant, and it's defined as a ratio between the diameter of a circle, that is the longest line going from one side of the circle through the center, ratio of the circumference, that is the distance around the circle to its diameter, or going across from there. So that ratio of its diameter is the diameter to the circumference to the diameter is defined as pi. But it was certainly was. And it was known, I think, in terms of doing measurements. I think they've gone out to, in the history of computing it physically, there were people that went out to about 6 digits, although their method might have been they sort of had an error in the 6th digit in trying to do that circle. But there are other ways to calculate pi, because pi is a constant. It's not just the circumference to diameter ratio, but it shows up in many different places. Many spots that are they're involved in physics and mathematics are quite it comes up quite frequently. So, and then there are formulas for deriving pi. People found, because pi shows up in lots of mathematics and lots of things in physics, people came up with ways to compute pi, not by the geometry of a circle, but by various formula. And the history of those formulas goes back quite a ways. Again, the circumference or diameter is one definition. Another is the area, right? If you have a circle that's 1 unit in radius, go from the center to the outside, is 1. The area of that circle turns out to be pi, because the area is pi r squared. If r is 1, 1 squared is 1, so the area becomes pi. But certainly in physics, there are things relating to the Heisenberg uncertainty principle, cosmological constant, Einstein's field equations, magnetic permeability of space, Kepler's laws of motion, the period of a pendulum, Coulomb's law of electric force, et cetera, et cetera, et cetera. A lot of these things come out where pi is integral integral into the formula. And in fact, there are integrals that you can calculate that produce pi, such as if you were to take the formula square root of 1 minus x squared, all square rooted, dx from -1 to 1 times 2 is pi.
Okay.
So there are various integrals you can do that can produce pi. But there's also various infinite series, right? That is, and one of the earliest notion of a thing is a formula we now call Leibniz formula. But we know that this formula was also known back even in the 1300s.
I think I actually used that formula to try and approximate pi back when I was first learning Java, and I put it into Java,
Sure.
and it took a long time to get something close. I think I got up to something like 4 digits were accurate before I decided, okay, this has taken an hour or two or something like that.
So that formula we're talking about, the sort of Leibniz, now we call Leibniz formula, because even though it was known perhaps, the formula for produce computing arctangent, right, was known for quite some time. It wasn't until Leibniz came around that actually proved it. People saw this formula in this particular series, but it wasn't until we started getting we had mathematical basis for which we understood this Leibniz formula. The problem with the Leibniz formula, as you said, it converges very, very slowly.
Yeah.
And so it's not something you would really want to use for that. But as I say, it does work. And sort of, so the arctangent of 1 is pi over 4. So one of the people were doing was computing arctangent, coming up with basically infinite series to compute arctangent, and you multiply by 4, and you get your thing. So for I believe if I recall the formula correctly, there is a for example, there's a formula that says 4 minus 4 over third plus 4 over 4 fifths minus 4 sevenths plus 4 ninths minus 4 ninths, altering back and forth, where it's 4 divided by that set turns out to be pi, and that converges very, very slowly. It will converge, but it's very slowly. Now, Euler came out and said, well, actually, there's a one that does slightly faster. And what he does is has the 1 plus a half plus a third plus a fourth minus a fifth plus a sixth plus a 7th plus an 8th plus a 9th minus a 10th plus 11th plus a 12th minus a 13th. So there are there are terms for which it's 1 over something, and other terms where there is minus 1 over something. And so in Euler's formula, it converges a little bit better. But we have much better ways of doing it now. Probably the string of so the question is, you can compute pi, but it takes a long time as you go for more and more and more terms, right? It's an infinite. You have essentially this infinite sequence of terms, and as you add more and more of those terms, you get a better approximation. But some of those convergence converge very slowly. They get to pi, they approach pi arbitrarily close, but they do it in such a painful way.
Yeah.
So there are better ways to approximate pi. And again, the Middle Ages, people were doing some some things again with physical calculations, but they began to express various formulas. For example, someone found that square root of 12 times the following: 1 minus 1 over 3 squared plus 5 times 1 over 5 times 3 squared plus minus 7 over 3 cubed. So okay, let me look back again. It's 1 minus 1 divided by 3 times 3 plus 1 divided by 5 times 3 squared minus 1 divided by 7 times 3 cubed plus 1 divided by 9 times 3 to the fourth, dot, dot, line. So you keep doing that, and you multiply that by the square root of 12, and you get pi. And that improved things a little bit. But it really wasn't until Ramanujan came around and had this extraordinary formula, which produces 1 divided by pi, and so you can do the reciprocal of it, and it converges relatively rapidly. And so a lot of them, modern quote records for calculating pi use this Ramanujan formula, which was proven. It's proven to converge to pi. It converges rapidly, not like the terms you used, and it will do a bit better job. And then there's people have improved on Ramanujan formula for a while. To now in January of last year, they used a modified formula to do pi to 50 trillion digits.
I have heard of the name Ramanujan. I think it might have been to do with ellipses. I think he has a formula for calculating, I think it's the area of an ellipse.
So yes, and Ramanujan shows up. He was extraordinarily gifted mathematician from India that had a really rich collaboration with a British mathematician, Hardy, and the two of them produced results. Ramanujan came up with things, and it was not just dabbling around with stuff in there, but proving that these things actually converge to pi was part of his among many things that Ramanujan is known for. His convergence to pi sequence is just one of them. He was a very great mathematician and so people use that technique. Now, just because you have a formula doesn't mean that you're able to hit record numbers. For example, in this approximations of things like if you have the terms whether n squared plus 1 divided by 4n cubed plus 5n, that thing as you keep n going out you use that to converge on pi. But now you have to calculate with lots of digits, and your typical computer calculator has only so many digits. So you've got to come up with a way to compute with more digits than your computer has in a single word memory. So that's called multi-precision calculations, and those. So people use efficient methods of computers calculating with lots of digits, combined with these approximations of pi, these infinite series of pi, by computing more and more terms that are proven to converge on pi, that some of these records are shown.
Yeah, because when it comes to trillions of digits, I'm trying to work out how much memory that would take up, and currently it's looking like it would take... so that would be 1 million, that would be 1 billion. It's looking like it would take up terabytes of memory, just as digits.
Now there are interesting other methods of doing so, but again, if you think about the naive way of doing things, if you think about how you were taught at school to add and subtract, multiply and divide, the digits of all the things and doing all the terms and so forth, and carry the 9, carry the 1, all that sort of stuff. You can have computers do that, and so you can have each memory cell be a digit, right, and go through the combinations of all the stuff to add and carry terms and multiply and all the cross products. It turns out the way that humans do it in school, it becomes extremely inefficient at the very, very large calculations that are done. Now, I should step back and say, there's nothing really, there's not very much in the way of mathematical interest when you start getting to 50 trillion decimal digits of pi. I mean, you're not gaining any new insights there.
Yeah.
Having a new formula that converges to pi would be interesting. Having the computational techniques to perform those calculations is also interesting because there's lots of other real-world problems that those techniques can help you in.
One of the things that I actually found interesting recently is I was watching a video which was talking about how pi to the pi to the pi to the pi to the pi could actually potentially be a rational number, but we don't know.
Well, yeah. So let's talk about one of the another thing I did, and that is not related to calculating pi, but to mathematics in general that I think is interesting is that we have various classifications for numbers. So there is the natural numbers, right? And I like to use the definition of natural number is the counting numbers, 1, 2, 3, 4, 5, down the line, right? The thing natural in terms of objects you can see. I have 1 rock, 2 rocks, 3 rocks, so forth. Now, the integers include the natural numbers, but they also include 0, which was a fairly late development in civilization, and then the negative numbers, right? The things less than 0. So the integers go -0 on up, but -1 on down, and those integers, although for a while people thought that negative numbers were ridiculous, they were sort of these absurd things, but it turns out they're actually
very useful,
quite useful, quite real, especially if you want to, let's say, buy a house and you don't have the money, so your net worth becomes negative from the loan, offset by the positive of the value of the house you own, type of thing.
Yeah,
so,
and also
in finance,
I was just going to say it also becomes very useful if you want to tell people that they're in debt.
Yes, and so or you're behind or something like that form. So the integers. So you have the natural numbers, one on the integers, which go back and forth. Again, all these things have an infinite number of elements. Right? There's no largest natural number. There is no largest integer. There is no smallest integer, with negative integer, right? So the integers are one thing. Well, then the next type but we have other values, right? If you look at number line, there are spots in between those whole numbers, and one of those things we call are rational numbers. Now, why do we call it rational? Well, because they're a ratio of 2 integers, like 3 divided by 2, or 1 divided by 7, or 17 divided by 459, or something like that form. These ratios of numbers, these rationals, now are pairs. And so, in fact, although one of the ratios on the number line you can't represent is dividing by 0. So as long as the denominator is not 0, you have a number on the top divided by a non-zero, an integer on the top divided by a non-zero integer on the bottom, you get a rational number.
Yeah.
And so, in fact, a lot of the methods of calculating pi involve, an infinite, these sort of infinite terms of rational numbers.
Yeah.
Right. Remember, we talked about 4 minus 4 over 3 plus 4 over 5 minus 4 over 7 down along the line. Those all are rational numbers. If you keep adding them together, it'll painfully go towards pi in a rather slow fashion. There are much better ways to do it.
Another irrational number that I know of is the square root of 2.
Okay, so rational numbers are the things where you have a ratio, and there actually have been some approximation of pi that have been where people used approximations pretty well. For example, 25 divided by 8 is 3.125. It's kind of close. But you can do better and show that, for example, 223 divided by 71 is a little less than pi, and 22 divided by 7 is a little bit more than pi. And so there's been other approximations. For example, in 400 ACE, someone showed that 111,035 divided by 53,329 is pi within 2 digits. Not bad. But someone else, 99 years later, said, well, hey, it's even easier if you do 62,832 divided by 20,000. Right? You get 4 digits. So there are rational approximations. You can get closer and closer. And so these things of the so-called power series of pi, the Leibniz formula of pi, even though it was first written about in 1400, it was Leibniz that showed that sequence converges to pi. But again, people found that to be rather slow, and so they came up with different formulas for calculating pi. And now, so we have the natural numbers, we have the whole the whole numbers, we have the integers, right, that are there, and then we have these rational numbers, which are things divided by things, as long as the thing on the denominator is not 0. Then you have a set of numbers called irrational, meaning they're not a ratio, they're a value. You can't take a number divided by number and get the value. And you mentioned square root of 2.
Yeah.
What number multiplied by itself equals 2? Well, the value is square root of 2. Well, you can prove that square root of 2, when multiplied by itself equals 2, cannot be a ratio of 2 numbers, right? It's a value, but you can't say something divided by something equals square root of 2. It'll always be a little bit off. And so the irrationals came about. But the irrationals do satisfy a formula. You say, I said, what thing squared equals 2? Well, you can solve that formula. It's the square root of 2, and that's the value. It turns out there are values for which a simple finite formula. What do you mean by formula? You're adding and multiplying, you're raising things to powers. That's parentheses, all that sort of stuff. And the expression is bounded. It's not like one of those terms where it's this plus this plus this plus this dot 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 dot. It's a finite number of formulas, finite number of terms. There are values for which you cannot represent them as any formula of finite size. And these are called transcendental numbers. So pi has been proven to be a transcendental number. There is no formula that of polynomials of stuff. You're dividing and multiplying and adding, subtracting, raising the powers with numbers. There's no formula that is of fixed size that equals exactly pi. In fact, it's been proven you cannot take. There exists no formula of polynomial formula that will produce exactly pi. There are formulas that get close. And you think about these terms, right? When you're doing these modern terms of adding more and more terms, getting closer and closer, you have this sequence of numbers that as you add them together get closer and closer. But all of those formulae don't equal pi. They get close to pi. But pi, so again, whole numbers, counting numbers, well understood. Rational numbers, things that are a ratio of 2 numbers. Then things that aren't a ratio of 2 numbers but are a result of a formula, like what thing times itself equals 8. Well, that's the square root of 8. That's an irrational number. And then there are numbers for which you can't take a formula of finite size of terms and produce it. Now, I'm talking about normal formulas. Yes, there's a formula for calculating pi. It's called pi, but they'll say no, that's cheating. Right? You can't take a polynomial of where you put in numbers, whole numbers, and you divide and multiply and add, subtract, raising the powers and all this stuff, and get pi. And so these transcendental numbers are really, really quite strange beasts, and we're still learning about transcendental numbers. But one of the properties of a transcendental number is that if you try to represent the value in base 10, our normal 10-digit stuff, you will never get a value, right? If you could, if there was a base 10 value that had a last digit, then that's a formula, right? Because what are digits? When I say 123, I'm talking about 1 times 10 to the first plus 2 times 10 to the 1 times 10 to the second plus 2 times 10 to the first plus 3 times 10 to the 0, right? The digits of a number are the polynomials of a base 10. That's why we call our counting thing base 10, right? The digits that you in a number. When you say I have 5,020, you say I have 5 times 10 to the 3,000 plus 2 times 10. Yeah. You build a formula to produce 5,020. So if you have a transcendental number, which is not the result of a formula, that means you cannot, in base 10, represent that number exactly. Otherwise, it wouldn't be transcendental. Does that make sense?
Yeah, that makes sense. I did want to say
remember again. Go ahead.
I did want to say a bit about what if you were to use base pi? Is that a thing?
Well, that's the thing that people ask, and people make an error statement. There's no last digit of pi, and the answer is that's one of my things when I have a T-shirt that says my pin is the last 4 digits of pi. The joke is, well, I didn't say what base it is, and so pi, as you say in base pi, is 10. So pi in base pi has a last digit. It's 0, right?
Yeah.
Done, right? And that's what I'm saying. What's the formula of pi? Well, pi. Well, that's not. Because what is 10? It's 1 times your base. If your base is pi, 1 times pi is pi. You can prove that pi to base pi is just 10.
Yeah. One of the
and so you have to be careful when you say there's no last digit of pi. You say there's no last digit of pi if the base is a rational base.
There is one
or
thing,
even irrational base.
There is one thing that I wanted to bring up, because one person said that a way to calculate pi was something like the cosine or the sine of something. It was I can't remember exactly what it was. Was it? But it was.
Well, there is the notion that the arctangent of 1 is pi over 4, right? And so the arcsine of and that's an example of the arc. You can talk about the arcsine as well, right? Because if the sine of pi over 4 is 1.
Well, actually, I found the thing that I was
arcsine of 1. No, is that right? No, the sine of pi over. Let me be careful here. I think you're right.
Yeah, I found arcs.
If it's the sine of pi.
The arc cosine of -1 is 3.1415925 radians.
Okay, let me correct myself. The sine of pi over 2 is 1. So the arcsine of 1 is pi over 2. So 2 times the arcsine of 1. Same thing. The arctangent of 1 is pi over 4. So 4 times the arctangent of 1 is pi. So there are ways like that, and all that stuff is really using trigonometric identities to deal with the ratio. But
Yeah, but one
I
one
apologize
person
for that.
one person says one person when I was mentioning about calculating pi, they said, "Isn't that They said something about, oh, you could just use this, but that's kind of cheating or something."
Again, as I say, it's so to be, if you're going to be mathematically precise, you say that a transitional number like pi has no last digit when expressed in a rational base, like base 10 or base 2 or base 5 or 7, or those things. Those things you can prove, because if the number did have a last digit in a base that's rational, then there's a formula to produce it, right?
Yeah.
But the transitional numbers aren't a result of formula like that. So the result is that it doesn't have. Now, for example, pi in base square root of pi is 100. And so in fact, there are an infinite number of bases for which pi has a last digit.
Yeah.
And they all involve bases that are that have pi in the formula. So you're kind of cheating. But it is interesting that we know that pi is transcendental. I don't believe it's known whether pi to the pi power is transcendental. And but people computed it and kind of shown that it's not integer, right? Because you can compute pi to the pi. Approximately, so that there's always, when you get down to the unit digits, there's more stuff, right? You to say it's not an integer means that when you get to the decimal point, there's more stuff. Yeah. You're not done. So pi to the pi we know is not an integer. It's not even, in fact, we can prove it's not even rational. Pi to the pi has been shown to be not an integer, but we don't know about pi raised to the pi raised to the pi raised to the pi power. That value is enormous value, even though you say, well, it's 3.14. By the time you've gone to the fourth level of exponentiation, you're dealing with calculations that are so enormous that they become fairly intractable even for computers. And
I saw a video recently where it was talking about this, and it's used the example of 3 to the power of 3. Well, 3 times 3 is 9, right?
Mm-hmm.
Then times 3 again, that's 27. And so that's 3 to the power of 3. But then to the power of 3 again, then it's, you get very big very quickly, because you basically, or no, it'll be 3 to the power of 27 is very, very big. It's got heaps of digits. But then 3 to the power of, I think it's like 7 trillion or something like that. You've got, that's 3 times 3 trillions of times. Or was it billion? I can't remember.
So 3 to the 3 to the 3 has 13 digits.
Yeah. And then
3 to the 3 is enormous, because that 3 to that 13 digit number is quite large. We can compute if we do the log of 3 times that exponent. We have a number that is, and let's take the integer of that thing. The number of digits of the number. So 3 to the 3 to the 3 to the 3 has an enormous number of digits, and the number of digits is 13 digits long, right? So you're over 10 trillion digits to represent 3 to the 3 to the 3 to the 3 power, right? So you say, well, what's wrong with 3.14 a little bit to the little bit to little bit isn't that value. Well, the problem is that if you just say 3.1 to 3.1 to 3.1, you'll find that that's a really bad approximation of pi to the pi to the pi. And by the time you get to pi to pi to pi to pi, four levels, you're way off. And so you end up having to calculate an enormous number of those digits down the line by the time you're raising to the power to the power to the power to power, and in dealing with enormous amounts of storage in order to get enough digits to make it accurate. Right? And so it's not simply a matter of you just calculate to the decimal point and stop, because otherwise you do 3 to 3 to 3, and that's not pi to pi to pi to pi, right? You have to go down those terms, down very deep into the decimal expansion of pi, and calculate with those things with enormous amounts of storage in order to try and calculate. And it is a pretty intractable, I wouldn't say it's impossible, but it's a pretty intractable problem to do a calculation just down to the decimal point. That would tell us whether or not it was integer or not. Now, you would say, well, wait a minute. How could a transitional number to a transitional number to a transitional number to a transitional number equal an integer? Well, e to the log 2 power is natural log 2 power is 2.
Yeah.
The definition of log, right? so that's a case of e, which is a transitional number, and natural log of 2, which is a transitional number. A transitional number to a transitional number power equals an integer. E to the natural log 2 power is 2.
Yes.
That's how it's defined. And you say, well, that's kind of cheating, right? But that's an example of a formula where a transitional number raised to a transitional number equals an integer.
Yep.
Now, you might say, wait, I thought you couldn't get a formula. Well, I'm talking about a formula where you have, it's a polynomial where the powers are integers, where the coefficients are integers, and you're plus, minus, dividing, timing, raising the power stuff. Not taking a transcendental number, because the problem is you have to take this natural log of 2 out infinite number of digits as the power of e out to infinite number of digits, and to get exactly 2, right? You can show mathematically it's there, but to calculate it, you need an infinite number of digits. So you have a formula that's infinite. So so this business of saying, well, something like 100 to the or like 10 to the common log of 10, right, is going to be a rational number. E to the natural log of 10 power is going to be 10. So those examples where you can take and put transitional numbers into formula and get an integer out.
Okay.
It hasn't been proven that pi to the pi to the pi to the pi, 4 levels, is an integer.
But it could be.
We don't know that. I would say it's safe to conjecture that almost certainly is not an integer, but you can't prove it.
Yeah, we just don't have the.
There's only thing to say. I don't think it is, but my opinion doesn't matter in mathematics. It's whether you can prove it or not.
It'd be like
one way. Go ahead.
I was gonna say it'd be like me saying, well, let's say that pi to the pi to the pi to the pi isn't a transcendental, isn't an integer, or something. But what about pi to the 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 pi? And I mean, when you get into that, you'd have to.
By the time you get to 5 levels, that calculation is going to be much better. So you probably what you need to do is to there are a number of conjectures regarding transitional numbers that are unproven, that if proven might give you a hope of stating something about pi to the pi and pi to pi to the pi and pi to pi to pi to pi. Those are possibilities. But again, that's a proof, not an opinion on things. So
yeah. Well, I mean,
again,
I suppose when we have a Dyson sphere, we'd be able to calculate, like a Dyson sphere around the sun, might be able to calculate all these things.
That Dyson sphere would have problems in terms of the rigidity of the structure. Even the stuff about of motion, and by the time you get to things that are in planet-sized stuff, you start getting warp space, because the mass of the Dyson sphere would begin to warp space. So you have to become fairly careful about how you measure stuff, geometrically speaking.
Okay.
I mean, if you're talking something about the things getting the mass of a planet, you start to get enough mass where the space-time gets warped around your mass, and then straight lines no longer are what you think they are geometrically speaking, and you start to get, if you're not careful. Also, the physical measurement of a circle, at some point on atomic level, you start to get to basic lumps of molecular structure, and where do you just kind of approximate where it is? I mean, because again, physical structures don't have the mathematical precision that a line does. I mean, a line is zero thickness, where physical structures are, at some point you got the lumps of the atoms, right? Where do you stop in your measurement? But we've produced very round things. The Gravity Probe B experiment. Look up Gravity Probe B. It had 4 spheres that were the roundest objects that people ever created, and quite possibly the roundest macroscopic objects. One of the most random objects in the known universe. And these were experiments to try to test general relativity, called Gravity Probe B, and it showed that general relativity was, it basically confirmed general relativity to experimental error. But those things required 4 very, very precise spheres rotating free in space to show something called space-time dragging. Anyway, so it's hard to get physical things to be round and stay round and not have pits and lumps and so forth.
I was just gonna say, imagine if, because we've got someone in the chat, or at least called Real M Biodome Concave Earth Apple, who thinks that he's debunked pi, and imagine if pi wasn't actually 3.1415. Imagine how many things would have to be thrown out there, or imagine how many people would go, hold on a second, why is this thing that's supposed to be the roundest thing in the universe, why is that not becoming as round as I'd like it to?
Sorry, in the known universe, but we have formulas to calculate pi. They happen to be these infinite, they require infinite number of an infinite series, and so that thing has been proven. It's not close. It is a case of 4 times 1/1 minus 1/3 plus 1/5 minus 1/7 down the line. That's one thing that Leibniz proved equals pi, right? And there's many other things that go on. Like, for example, there's a lovely formula for arctangent, and it goes 1 plus 1/3 plus 1 times 2 over 3 times 5 plus 1 times 2 times 3 over 3 times 5 times 7. The next one is 1, next term, and the top is 1 times 2 times 3 times 4. The bottom is 3 times 5 times 7 times 9. So what you're doing is you're taking the numerator is a factorial, 1, 2, 3, 4, 5, blah, 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 down the line. The denominator are the products of the odd numbers, and you add those terms up, you multiply 2, and you get pi, and it's been proven, right? There's no ifs, ands, or buts. it is a fact. And so you can approximate pi these ways. And, and it's so for example, while we were waiting on the show, I used calc to calculate pi to 100,000 decimal places. It took only, I only waited for a couple of minutes, and it came out to 100,000 decimal digits, and it's accurate to 100,000 digits, right? Right now, while the show is going on, I'm doing the same calculation out to 1,000,000 decimal digits. Again, that's not pi. It's accurate to that many terms, but there's an error term that always is there because, again, pi is transcendental, and you never can get a rational base like 10 to exactly equal pi.
Well, with this program here that I've got, so this is a very simple program. It's and it basically what it does is it makes a circle and calculates the circumference. Well, it actually makes a quarter circle, right, and calculates the circumference of that.
No.
And so if I type in 1, that will basically have a radius of 1, right? And so we'll work out the hypotenuse between the point here and the point here, and so it should be the square root of, so it should be 1 plus, so it'll be 1 squared plus 1 squared. And so it should be. Is it? No, I don't think. No, it should be 2 times the square root of 2 or something like that. I can't remember. What is the square root of 2? Let me. Square root of 2. Yeah. So
there's been formulas that have been produced that are proven to be pi, that are an infinite sum of terms that converge on pi and have been proven that way. And there's some very interesting stuff. For example, there's a very interesting formula that allows you to compute a binary digit or hexagonal digit of pi way far out, right? It allows you to compute that formula independent of the other digits.
Okay.
And the reason why this works is that this infinite series has a term 1/16 to an integer power times an expression. So you evaluate the expression, you know the hexadecimal digit at that spot. Of course, each thing has to be evaluated independently, and it's not. So, there's a paper that was published by Bailey et al. In 1997 for a new formula for pi, and because you can factor out a power of 16, a negative power of 16, when you compute that term, you know the hexadecimal digit, base 16 digit of that value. Of course, you have to compute all the terms up there, so it's not an easy expression, but it is definitely a tentative expression again that you can do. So there are many ways that you can calculate pi, because pi is more than just the ratio of the circumference of diameter. Pi is a value that is very rich in mathematics and in numerical computation, computing pi using a proven infinite series that again, it's a formula, but it's infinite length. So you have to keep calculating. You never get the pi, but you get close to it. And there's some pi formulas that can get to there very fast, much more than that the Leibniz formula that you talked about.
And probably much faster than this here. Like this here currently I've calculated out to I think it's about 6 to 7 decimal places, but your formula did 100,000 in 2 minutes, so that puts mine to shame.
And by the way, that formula I'm using is not the modern efficient stuff. That, for example, people like to I think I'm pronouncing the name poorly, Chudnovsky algorithm, that has this thing where you can where it's shown to produce 1 over pi, and you just do the reciprocal, and you get your digits. It converges very rapidly, and it does really, really well. Gauss, there's a Gauss-Legendre. So the Leibniz formula was used in the 1300s, but you have something for ability to do this binary splitting of the arctangent series that was done in the 60s, and by mid-70s you had a Gauss-Legendre algorithm that was pretty good, but it was improved quite a bit by the Chudnovsky algorithm, again based upon stuff relating to Ramanujan's work. So the PyHex project, there's a project out there, a network of several hundred computers, just finishing computing the 5 trillionth, the 40 trillionth, and the quadrillionth bit of pi.
Oh,
so
wow.
Pi in binary, they've gone up to 10 to the 15th bits by computing that bit out there. And by the way, all those are 0. So the 5 trillionth bit, the 40 trillionth bit, and the 1 quadrillionth, that is 1,000 trillionth bit of the binary convention of pi is 0. And so those are things where they know what that bit is, and they'd have to do a similar work to get the next bit and the previous bit. So it's actually a lot of work to compute pi by bit or by hex digit, because you have to do it again and again and again and again. But if you're curious about what an actual bit is, there's formulas to do a lot of work to get us in that spawn.
Yeah. This is currently, I'm not sure if it loses precision at 1 billion or 100 million when I type in that number for the radius, but this does lose precision quite quickly and I think I've typed in the number which it loses precision at, because let me quit that and go 100 million, because I know that at 100 million it's almost pi, but it's...
Yeah. But you should probably look at something. For example, there are a number of codes out there that you can look at for something called PiFast, QuickPi, SuperPi, are examples of stuff where those codes you get to do these calculations. Again, the value of or the importance of computing pi to a lot of digits is more of a curiosity. The technique is what's important. So many things in mathematics, the answer is less important than the technique. It's one of the reasons why in mathematics it's important to show your work, because your work is often more important than the result.
Yeah.
Right? If there's what's the umpteenth illionth digit of pi, and you get a number, you say, well, how did you do that? Show your work. How do you know that? What do you do to verify that? That's more valuable than the actual answer.
It's like,
because again, in science, often
a lot of people in maths class always asked, why is it important that I show my work? Like, why is it important that I show my work? And isn't it important that I just get the right answer? And my response, I think I used to have that attitude, but my response these days would be, well, let's say that you got the wrong answer, right? But you made a mistake somewhere down the road to get the wrong answer. Let's say that everything was perfect, but maybe you hit 9 twice instead of the one time that you're supposed to hit it. And then you get an answer that's way off. Now, if you've got the right technique, you will still get marks for that. But if you've got the... but if you just give the answer and your answer's wrong and you don't have any workings, then you don't get any marks.
Yeah. Well, and again, science, I talk about science rather than specifically mathematics. And science is about questions, right? Science values questions more than answers, right? And in fact, the great scientists are the people who were able to ask the right question to the right people at the right time. And it's the questions, and if you happen to get an answer, that happens to be just a stopgap to produce more questions. And so again, in mathematics, to prove that pi to the pi to the pi to the pi is not an integer, which is almost certainly the case, to prove that is more important. The method you prove it is more important than the answer yes or no. Right? It pi to the pi to the pi to the pi an integer. The answer is going to be yes or no. And the answer is almost irrelevant. The techniques to prove it are what's of value in there. So again, showing your work is also because someone can benefit from your work and improve on it. So when I, I'm known for having had held or co-held the world record for record type primes of twin primes and large known primes, and the prime itself was curious, but it was not as important as the technique that we developed to prove the primality of that number.
Yeah.
And the world record for discovering the largest known prime goes to the first person to correctly prove the number is prime, not simply to state, I think it's prime. Same sort of thing. If you come up with an image series that is going to converge to pi faster and more efficiently, allowing people to compute it to more digits of some base faster, that is more interesting than what the actual value of pi you produce is.
I think you might know... I don't know if you're familiar with this program here that I've got up on screen. It's called Prime 95.
Okay. Okay, yes.
So yeah, essentially it's to try and find Mersenne primes, and apparently you can... Although I do think that it's probably very unlikely for me to stumble across a prime with this program, as they're very rare, very rare.
So earlier on in my career, when I was 17 and 18 years old, I co-discovered two Mersenne primes. Now that are quite small, but the time was record at the time. And then 10 years later, in the group called Omdal 6, we proved a number which is not a Mersenne prime. We basically dethroned the Mersennes and came up with a number, showed a technique for that. In fact, if you look, I have on my website, and maybe we can add this to the list, a presentation, a presentation that talks about the modern, basically the best modern techniques for proving very large numbers and about finding a new largest known prime. It turns out that the prime 95 has a simple algorithm, but it is not the most efficient way to find a new largest known prime.
Okay.
And you can actually beat the entire group of people looking for Mersennes. And again, that's a nice thing to do that they're doing, is of doing calculations and beat them to a record using more modest techniques compared with all the computers, because you can compute smarter rather than harder, right? And when I've had the world records or co-held world records relating to large primes, it was never on the fastest machine. I never had the fastest machine, but we had the smartest, most efficient method for proving primality and getting it confirmed. That's the That's the thing. So there are techniques, and so if you look at my in my paper, again, it's a PDF file that I keep up to date. And occasionally, I'll do public talks where I give a class on this thing. I'll put it into the I'll put the link down here so that you can post it. I'll put it into the Discord thing. If you look at that thing, it's called a Grand Coding Challenge, Finding a New Largest Known Prime. That paper, without really, it doesn't go into really deep math stuff. So it's not a heavy math paper at all. If you can divide and take a remainder and do things like that, you can employ the techniques. And so it talks about how you go about finding a new largest known prime. And the answer is almost certainly that you can beat the Mersenne, you can dethrone the Mersenne primes again by proving a primality of a number that's a little bit bigger than the current record, and it's out there for someone to do. So that technique we'll go through. It talks about the prime numbers and history of stuff and about the history of the stuff. It explains about the Lucas-Lambert test that Prime 95 is using, and then it goes into a modern calculation techniques using Fourier transforms, and then it shows that you can find. It talks about there's an award out, right? That I am on what's called the Cooperative Computing Award, and the first person to correctly prove a prime number with at least 100 million digits, there's a $150,000 award for the first person to correctly prove that.
Okay.
And for the person to prove a prime with at least 1 billion digits, 10 to the 9th, there's a $250,000 award out for that. Both of those are unclaimed at this moment. The 1 million digit award and 10 million digit award were claimed in 2000, 2009. But the progress is sort of stalled there. We had hoped that the 100 million digit record would have fallen by now, but people have kind of gotten behind. And I think one of the things is that the techniques people are using are not that efficient. To do the calculations necessary to prove 100 million digit, a number, by the way, it doesn't have to be 100 million digits. If it's 100,050,000, right, it has to be 100 million digits or more.
Yeah.
To get the award. And by the way, the other thing you have to do is you have to prove it, right? So you can't sit there and say, here's a big number, it's prime, give me the money. It's like, no, you have to actually publish a proof in a peer-reviewed journal of mathematics and have peer-reviewed people saying, yes, your proof is correct. And people verify your results before you get the numbers. You just can't just claim something. You have to prove it. And why do we force you to publish it? Because the technique is more important than the answer.
Yeah.
So say this enormous number is prime. Okay, that's kind of curious. How did you do it?
Yeah.
Publish your result. Fully disclose your method. Let someone else take and learn from your techniques and improve on it. That's the nature of science, right?
So
that's where this thing.
I was just going to say, so if I steal your method, can I say, so the way that I proved it was by stealing Landon Noll's?
If you do that, that's fine. Because I'm one of the people on the advisory committee that looks at the stuff and tells EFF whether we think that the proof is valid or not, and whether.
Okay.
And part of the thing is we say, give us an abstract of the publication of the mathematical journal in which it has been proven. We'll read the thing and see if it passes our sniff test and so forth. But anyway, as a result of my being on the advisory board committee, I'm not eligible. Right? So I can't turn around and say I believe myself. Right? That's no. I'm not eligible. So I'm not in the game of finding that set. I think it'd be a shame if people just brute force their way into the Mersenne lottery. And again, people are doing marvelous work, but right now it is a problem of, can you get enough computers to test enough numbers to find one of the Mersennes that numbers that happen to be prime. And they're getting rarer and rarer and rarer. But there are other formula, an integer times 2 to the power minus 1, which can allow you to find a large prime much faster than just 2 to the power minus 1. So multiple of a power of 2 minus 1, the techniques for finding that are actually better in finding a new largest known prime than you do under Mersenne, because Mersennes are so rare. 2 to the power minus 1 being prime is very rare and getting vanishingly rare. You have to do more and more and more tests before you find something. Whereas if a constant integer times a power of 2 minus 1 has a predicate that constant integer is not trivial, like 1 or 3, but it's a so for example, Amdahl, we showed 391581 times 2 to the 2131, 216193 power minus 1 was prime. That it's a 6-digit number times 2 to a 6-digit number minus 1 was prime. We proved that, and that was faster than finding the next Mersenne.
Okay.
But I'll just say, if you go through that stuff, you'll see the advantage of looking at numbers of the form h times 2 to the minus 1, and testing for those is much better than that. And the techniques you can do are there. And so there are some new techniques coming out that I hope to co-publish as well that allow you to do some interesting stuff in computation. And again, it's the technique that's more important than the answer.
Speaking of things being faster, there's actually something that I'm rather curious about, right? And so if I just edit this for a second, and let's say I create a Boolean variable, and I set it to equal. Let's actually create two variables. We'll go int a equals 100,000, int b equals 2,000, and then I say Boolean c equals a equal to b. Right now, do I need to increase this? Wait, can I increase?
I'm trying to look at your size here in the.
If I do this, you should be a little bit easier to see that, right?
Let's see. Let me get this. Let me put this up bigger, because the problem is that on Discord it's showing me the live thing here. Okay, here it is. Okay, now I see it. Okay.
Yeah.
Go ahead.
So the next thing that I'm going to do is I'm going to just say let's say I want it to become b times 2, and then I want b to equal a divided by 4, and then I want, just random stuff. Then I'll go if c, and then do whatever there. Now, I want to know if that would be faster, if doing this would be faster than going, than if we had, let's grab this and put it down here, then if I had, if a is equal to b, and then right here. So would this be faster than that? So would this? Because I know that I know that comparing two things is generally pretty slow, and you've mentioned before how Intel decide to do, okay, when you've got a comparative thing. When you've got branching code, it'll check. They actually sometimes do the thing where they go down both paths before, and then when they get the result back, they just choose the path that is correct.
But it's going to be dependent again on. So by faster, I assume you talk about a computer And by computer, you soon talk about potentially compiled code versus interpretive code.
Yep.
So in something which compile into assembly language, the A equals B is where A and B are both registers, is a single op, single clock cycle.
Okay.
Now, the thing is, if A and B are not fit in registers, but are large strings of characters, then you have to do there are sort of different instructions to get that efficiency to determine that. So it kind of depends on what you're talking about. In the case of two integers, comparing two integers, if it's compiled, your compiler should result in a piece of code which would say the following, right? The one level of compiling would say, load 1,000 to one register, load 2,000 to other register, do a register to compare, and the result will be a bit in the status word. Now, a better compiler would sit there and say, well, I can do the calculation and just optimize that routine to return false. Right? That would be there's actually a calculation where you do the calculation and you run the program and just returns false, right? Because it can evaluate the calculation during compilation time and result in program just returns false.
Okay.
Now, it's different than say if I have two strings that are megabyte in length. And I've had that are megabytes type strings, and I want to compare those two strings. Well, now the thing you do is a couple of things. You can do a simple thing. The first thing is, if you have the string, do you know how long it is? Right? Are you merely given a beginning of the string and some notion that you'll find a sentinel that you'll find the end, or is it that you know the length? Because if you have two strings and you know the length, the first thing you ask is, are the lengths equal? If they're not equal, the strings are not the same, you return false. So you just compare the lengths. The next thing becomes, if they are the same length, then you start comparing blocks of that string. Here, however, it becomes an issue in processing. The answer you have for 100-character string is different than the answer for a 1,000,000-character string. That's different than the answer for a 1,000,000,000,000-character string. What do I mean by that? Well, a 100-character string in some modern CPUs, there are 5 to 12-bit instructions that can do comparisons of large blocks of stuff very efficiently in hardware and get you an answer in a few opcodes. When you get to 1,000,000 byte strings, things of that length, the next thing you got to do is worry about getting most likely your strings are out in main memory and pulling that memory into the processor in order to do comparisons. And one of the things in particular you might want to do is turn off what's called caching, because in modern processors, the CPU is so much faster than memory that what it does is it tries to not bring in single values out of memory, but whole chunks of things in memory, because it's assuming that what you're going to do is go to the next value. So you might start doing processor stuff where you're loading blocks of main memory into the processor to do comparison, and when you're done with that, throw that away. You don't try to essentially keep your cache going, because you end up slowing down other calculations. So playing with cache is something. By the time you get to, let's talk about a string where there's terabytes long, and let's assume you don't have a computer with terabytes of memory. Now that computer is probably on secondary storage, and now you have a storage problem of getting from storage devices through a network into the memory to then feed into a processor to do a comparison. And so how you do things on that scale is a very different set of calculations. And what it turns down to, when you get to very, very enormous large strings, is that you start to get to a program is dominated by the network and storage. So if I had a copy of the 50 trillion digits of pi, decimal digits of pi, that are known, and you had a copy, we wanted to know whether or not we're the same. We wanted to prove that my copy and your copy are identical. Beyond a shadow of doubt, there's techniques you can do. You can try to I can try to hash mine, you try to hash yours, and if our hashes match, they might be equal. But if I have a large block of memory, you have a block of memory, and we're going to compare them and know precisely that they are the same, we've got to start, some entity has to get both things together in order to do the comparison.
Yeah.
Because having the same hash doesn't mean you've proven that it's the same value. It's just likely to have the same value. So now it becomes a case of, if I've got a 10 terabyte file on my drives, my RAID farm, you have a 10 terabyte file approximately on your side. We both agree that the same length. We both agree that we run the hash, that we get the same hash value. Now it's likely that they're likely they're the same. Now we've got to start exchanging chunks, or one has to give the chunk to another, and do those comparisons. And how you do the comparisons is also a fairly intensive thing when you get to those scales. So computing on those large scales involves more than just writing a piece of code. And almost certainly, if you have to do comparisons on the terabyte to petabyte scale, you are almost certainly, you might involve some novel hardware as well as specialized machine code.
You did mention hash. Yeah.
Yes, go ahead.
I was just going to say, you did mention hashes before, and one thing that we used cryptographic hashes for this document to basically. So here we go. So essentially, this is, you may have received this from Mark Leventhal, from the Director of Earth-Shaped Counterintelligence, right? And it's got all these things, and basically says that people like myself are paid by NASA to make YouTube videos about the Earth not being flat. But that's only on page 1. When it comes down to page 2, it says, just kidding, this is all a hoax to trap the gullible, no one gets paid, and all that. And then it says, end cryptographically secure message digest with this line, and then it says how to basically verify that all this here was in the message, and it has 3 different hashes. And it's one of them things where it's very...
And so they're doing, let's see, they're doing a SHA-256, SHA-356, and a SHA-512. So they're doing 3 different hashes. And of course, that doesn't prove it, because one of the things that people do in cryptic hash work is to estimate the area, the time and complexity necessary to find 2 different values that hash to the same thing in cryptographic hashes. Cryptographic hash takes a big thing and turns it into a thing of a fixed size, a many to one mapping. Many things map to 1. By that meaning, there is more than one value that hash to the same value.
Yeah.
There's 2 different objects, more than one object that turns into that hash.
But you
and so the likelihood of you finding that with cryptographic hashes hopefully is small.
With this, you got to also consider the likelihood of 3 different hashes, something beyond.
I mean, the SHA-256 and the SHA hashes, I'm thinking about, I'm trying to think, because the SHA-256 is really a SHA-2 hash, and the SHA-3 hash has a slightly different structure, but the SHA-512.256 is a slightly different structure. The thing you'd worry about with those things is proving that the algorithms are orthogonal. And I don't think it's been proven that way. I would think that it'd be computationally very difficult to find another document that has identical 3 hashes. It's not impossible, but it's difficult. There is a lot of work done in hashes, and I have online. I will share with you a cryptographic hash requirements. Here's a paper. Let me put it into the stream here. This is a paper that I have, and it talks about the too many demands of a single cryptographic hash function to satisfy, and it goes through a whole pile of things that people want hash functions to do, and there are in that paper 20 different properties that people want hash functions to do, and it's very difficult for any one hash function to satisfy everything.
Okay.
And so that thing goes along with at least 20 different things that people want hash functions to do, and the designing an algorithm to fit all 20 is extremely difficult. But right now, the current SHA-3 hashes are deemed for right now to be pretty good, but breaks only make them worse. And so 20 years from now, we'll probably be saying, yeah, no, maybe.
I do have a question. So does the FNV hash function, how many of those things does it satisfy?
The FNV, called Fowler-Noll hash, I'm the N in FNV, is not a cryptographic function. The purpose of the FNV hash is, so it's not a cryptographic function, right? And you can, with work, invert it, and you can find hash collision. The thing about, in fact, there's a challenge there's very challenging to find things like the values that FNV hash to 0 and other things. The purpose of FNV is to give you in a very short amount of computation, a value which is very well dispersed. So it meant that strings that are very similar will very quickly hash to radically different values. And you say, what do you mean by, what would you mean by similar strings? Well, if you took a bunch of URLs of a website that all going to be in with http:// something hostname.com/something, right? You'd have a lot of strings that are very similar. If you were to hash those things, the beginning things aren't going to help you, right? If you're hashing IP addresses, thing, let's say IPv4, or even IPv6 stuff, those strings you're going to have are very similar. And if you want to have a hash function that very quickly gives you radically different values, cryptographic hashes are so computationally expensive as to not be very worth it. So it's one of the reasons why, for example, Twitter has a problem of trying to identify strings and tweets by a handle. And so Twitter uses FNV hash. The 280 characters, 140 characters, oftentimes are very similar. And so Twitter makes use of like URLs to turn into a cookie by using FNV hash because it's extremely efficient. It's not meant to be something that is unforgeable. It's meant to give you a value that if you put into a bucket is very good at getting you a different value without stuff. So you only really have to do an add and a multiply for every byte of values, and that sequence gives you a very, very rapid conversion. So hash functions have purposes. Most of the time, it's giving a little thing to represent a big thing. And you don't care that there are many big things that have the same little thing. You want to be sure that the little thing you have is unique.
Yeah. Especially when it comes to things like passwords. I know that one of the purposes of hashes there is because it has the added benefit of not being human readable when you hash a password. Although one of the things that is also recommended that you do is you salt your passwords as well, because
Yeah.
What's that?
For example, in many modern Unix Linux systems, the password file, which says when you log in, you type your username and password, is it you? Rather than storing your password on the machine to say, well, is the password what we gave it to you as? That's bad because someone finds that file, they can read your passwords, right? And so instead, what often people would do would be to take and compute something. And one of the common techniques is to take a well-known constant like 0 or some other, something like, A, B, C, D, E, F, G, take that message, encrypt it with a hash of your password. So you take your password, hash it to a known value, like let's say compute a 256-bit hash of your password, and use that hash to then encrypt the number 0. So what you store in the file is the encryption of the number 0.
Oh, okay.
You know, and you know what the number is. You know what the answer is, 0. But what you do is when you log in, here's again, this would be an example of stuff where you type in your username and says, yeah, I know who you are. Okay, type in a password. I take your string, however long it is. I can produce a 256-bit hash. Use a 256 hash to encrypt a known string like 1, 2, 3, 4, 6, 7, 8, 9, blah, blah, blah. And when I encrypt that number, I get a blob and compare it to what's on the file. So if you see what's in the file, you just see an encrypted value of 0. You don't know what key it is. So your password hashed becomes a key to encrypt a known value.
Okay.
Now, the problem, of course, is that if you and I pick the same password, then the hash of the same password will be the same.
Yep.
And the encryption using that key is the same. So you don't want to do that. You want to have it be different. So instead of saying, I want to encrypt or hash my password, let's say instead, I will hash the password, comma, my username. Which means if I have the same password as you, the hash of my username, which is different than your username, along with our same password, will give us a different value, which will then encrypt, let's say, a constant, like A, B, C, D, F, G, H, I. It'll encrypt that constant with a different key. So again, that's called salting, where what it means is that the chances that you and I, if we even pick the same password, because we now mix in our username to that password, means that the password file won't show the same string. Now, you can go beyond that even farther. You can sit there and say, all right, I'm going to take my password, how long I want, my username, and some number. I'll pick a random 20-digit number. And I'll hash all 3 of those. I'll turn that into, let's say, a 256 or 512-bit value, which I go to a block cipher to encrypt a known string. And here's what I'll do. On the staff password file, I will store the original string. I'll store the constant. I'll store the encryption of the hash, which is your password, your username, the string, and the constant, jam them together, right? I'll put that together and compare the two. So now what it means is that if you crack my password, it doesn't help you very much to crack your password.
Yeah.
Right? You could brute force look for something to match against my encrypted string, and if you find it, you get my password. But that doesn't help you much for your string. You have to do the same effort because you're using a different set of inputs. So So in your password file, take a known blob to say, this is what I encrypt. There's no harm in knowing that. Take another constant, some random string that says, take that random string, merge it with my my username, merge it with my password, generate a hash, encrypt the known string to produce a known value. And if the values match, I'm proving. So what you're saying is, if I'm able to type in my username and password, and it goes through, picks up the known string, picks up the known constant, does encrypt, does a hashing, does encryption, gets the same value, then you let me in.
Yeah.
And if you get a hold of that password file, you don't see my password. You just see the encryption of something you don't know the key. So you can actually go through the key until you find it. But now the work you've done for me doesn't help you to find it for your password. Does that make sense?
Yeah, that makes sense. Like I have done a little bit on. So when I was doing my IT degree, one of the topics for security that we all got to choose a topic for security, and one of the topics the topic that I chose was cryptography, right? Mm-hmm. And that was actually, it was because the teacher said, "Oh, this is a really confusing topic," and I was like, "Okay, let's see how confusing it really is." And it's like, the concepts behind it were all very simple. Now, the algorithms and all that are rather complicated, sure. But I mean, we've been using cryptography for ages, since back in the days of, since back when we were using the Caesar cipher, right? That's a form of cryptography.
Yeah.
And so, it's just that we've gotten better at, what's the word? At encrypting stuff.
In particular, there's a branch called cryptology, which is the logic of encryption. And we've gotten better at cryptology of building functions that are resistant to cryptanalysis. That's the attack of stuff. So again, in a password file, if I said, here is the result of encrypting the number 0. And if you guess what key it is, you can derive my password. That breaking that is harder than simply just saying, I'm going to keep the password secret and hope no one looks at it. So as a programmer, you don't code the secret key into your code. You don't stick the secret into a database. You stick the result of a cryptanalytic function that, if you get the same value, means you almost certainly have the same inputs. So what goes into a login is who you are, what you know, some known circumstance around it, goes through a cryptographic function, produces a result. If the result is the same as when your account was set up, you're let in.
Yeah.
That's one form of authentication. There's many other forms, but that's certainly one form of authentication. So the question is, well, what function do you use? And the answer would certainly almost, might involve block ciphers or stream ciphers and or hash functions that are cryptographic in nature.
Yeah. I also know that even those can sometimes, even just having a password these days can be, cannot quite work out. So they also recommend that you use things like two-factor authentication, especially if you've got a password like password. If your password is password1, then the only thing that's going to save... I'm not even sure that two-factor authentication will be able to save that, but that's the only thing that could possibly... even attempt to come anywhere near saving that.
Yeah. But, being able to brute force trying all the passwords, right, is something that is relatively, has gotten much better, right? You might sit there and say, well, if I have a 10-character password, how in the world could the combinations be enormous? Well, the answer is, well, there's actually fairly efficient ways to do password cracking, right? If I have a known algorithm that says, password, algorithm, result. Did it guess your password? Right? That is inverting a password file. You'll be surprised at how many characters are resilient. My recommendation for if you must use a password is to also use multi-factor. So it's not only what you know, but what you have and something about you that becomes part of the authentication, right? So the problem with passwords alone is if I know your password and that's the only thing that protects your element, your thing you're trying to protect. If that's the only thing that's there, then if I know your password, you've been hacked. Now let's say I have to know your password and I have to have something you have, and I have to have something that you experience or something in your environment. That becomes a more practical thing. And so when you hear about two-factor, they're saying what you know, what you have, and who you are. Now, the problem is that there's some really bad ways of doing it, where they sit there and say, okay, you type in your password and the color of your first automobile. Well, I mean, how many colors of automobiles are there, right? And if I can multiple guess stuff, and or the name of your first grammar school, right? That can be social media derived. So if you have to set up authentication and they do something like have those stupid security questions, lie about the question.
Yeah.
So someone says, when they say, what is the name of your favorite pet? The answer is another long string that I keep as part of my authentication, right? You have to, right? That's another thing that you have to kind of know. But that again, just relying on a secret is a problem, because the bottom problem is once I tell you what the password is, I've lost the protection. So you need to know something. It's better to have something you know, something you have. Like maybe you have some kind of device that produces a result. That if you don't have this device, it's hard to invert. So I have to know something. I have to have something, and maybe it's where I am. That the combination of the two gets to be more resilient.
Yeah.
And then on top of that, you need to have various ways of saying, hey, someone's just authenticated as you. Is that okay, right? So you need to be able to because the problem with just password protection alone is I can offline have massive set of computers to crack your password. You don't even know you're being hacked, and once I have your password, you've lost the thing.
Yeah.
So instead, if there's a combination of stuff, the first thing you want to be able to do is to know that that the attack is being attempted. So guessing wrong should trigger an alert saying you've had these wrong guesses.
Yeah.
The second thing could be something like, say that if I'm able to guess all the things and all the things that make your identity, at least have a record you've been had. Because the worst thing is to have been cracked and you don't even know it.
That's why whenever I log into something, I get like if I log into Twitter on Firefox, even if it's from the computer where I'm logged into Twitter on Google Chrome, what comes up is it comes up with it basically says, there's been a new login from this device, and so I can just check and go, yeah, that's me. And then rather,
of course, you always want to sit there and say, well, how do you defeat that? And one of the answers is that if it's sending us to your phone number, then what I do is I change your phone number to be my phone number.
Yeah.
Now you don't get the messages, right? Now, if they're smart, they send you a message saying, hey, your phone number has been changed from blah to blah. And you say, wait a minute, that didn't happen. That would be a smart thing to do. But imagine you lose your phone. Or imagine you move and you no longer can use that phone number. Well, you want to have a way of changing your phone number. And so you have to be able to change your phone number. So if you can change your phone number because you lost your old phone or you don't have your old phone number, I can try to do the same thing. I can try to social engineer to convince them that you need to change your phone number, and I'm you, and that phone number is blah, right? Another way is that message that's going through the network could be captured and diverted, right? So the network message that sends a message to your phone saying someone's trying to log into your machine, you redirect that message to someplace else where the person says, "Yep." Cool. You don't see it. They don't see it. So you gotta think about all these things as far as it. That's one of the reasons why theft of phone numbers is on the rise. It's not that people want your phone so they can get your calls you get. It's because many times people use their phone as a second factor authentication. And so if I can convince a phone company that's my number and I want to change it, or I convince the company, like social media thing, that you have a new phone number, then you need to have other things going forward. It's all this part of defense and depth.
Yeah, it's one of them things that is very, very complicated when you get down to trying to stop people from stealing your info.
Sure.
But if I was sponsored by Nord, I just want to say, if I was sponsored by NordVPN, this would be a great segment too.
Yeah. So there's a case where, and I'm not sponsored by these people, but I put in the password. It's #1password.com. 1password.com is a group of folks that has tools that can allow you to keep track of passwords. And so. I have over 500 different types of passwords, and none of them are the same.
Oh, wow.
And all of them are 20 characters or more with symbols and other things involved in it. And it means that if someone compromises Twitter and gets the database, let's say they store my Twitter password in a really dumb way, and they're able to invert that, I just lose a Twitter password. I don't lose my Discord password. I don't lose my important account password, right? It's been diverse. And so 1Password is a tool, these are called password managers, that has a lot of work gone into it. Again, I'm not paid by them. I just like the tool. They're multi-platform, and they're very clueful people, right? Their product is excellent. So check out 1Password. It's a paid product, but it's paid because you're paying people to worry about some of those very fine details. One of the things you could do with 1Password, again, this is not a paid advertising, it's just, I like the product, is they maintain a database of vulnerable passwords. What's a vulnerable password? Well, when a bank gets digitally pillaged or a department store gets all their customer information disclosed. One of the things that often happens is the passwords or the pins that people use are disclosed, and so there's databases out there of known passwords, right? And what 1Password can do is look at your password and say, does your password match one of the passwords that's been known to have been exploited? You might find that a number of your passwords you think are clever aren't.
Okay.
Now, they do that not by sending your password someplace, but by computing the hashes of these databases and saying, in your computer, does your password you've typed in match a hash of a known exploited password?
Oh, I've actually seen.
So if you Go ahead.
I was gonna say I think I've seen something like this. Like what they do is they calculate the hash, right? And then I think the first thing that they do is they compare like the end of the hash to see if the end of the hash matches.
Yep.
Yeah. And
the thing, but you want to be sure it's done locally. Like some of the mistakes of people like LastPass is another thing that some people use. I don't recommend them because they have made some security mistakes that I think are unforgivable. Now, I'm sure they fixed those things, but I think that the 1Password people are more clueful in that sense. Not to say that they can't be broken as well, but that's an example of a password manager that can keep all your passwords and your identity information and stuff separate. But again, people talk about biometrics is another thing, and the problem with biometrics is that biometrics are a really lousy password, oftentimes. Right? Fingerprints. People, and there's a mistake. People think a fingerprint is somehow a password. No, one of the problems is that fingerprints, you leave them all over the place, right? You're, and you can't. It's hard to change your fingerprint, right? It's technically possible with finger transplants, but it's hard to change your fingerprint, and you leave them around all the time. And the fingerprint readers are easy to fool. One thing I did the security firm is the people who I think I can say this, that the producers of Mythbusters came to us and said, how easy is it to break a fingerprint reader? And we showed them several fairly easy techniques using stuff you can find in your kitchen to break some very so-called sophisticated fingerprint readers. Now, the two Mythbuster guys didn't know our technique, but what we showed the editor, the producers, was if you think about it, and these guys are clever, they should be able to come up with a way. And so they came up with it a slightly different way than we did in exploiting stuff. But again, fingerprint readers on a keyboard is one of the dumbest things I can think of, because your keyboard is full of copies of your password. So what is a fingerprint? A fingerprint is a name, not a secret. So what makes sense is to say, I will authenticate by my name, my fingerprint, which is part of my name, and some secret that I type in, and something I have, maybe some sort of token thing that produces a value. Now you're talking about something a little better. But biometric stuff oftentimes is only a good alias for your name. Your name is not secret.
Yeah.
Nor is your face. Nor is your... And by the way, if you use Zoom, your voice and your face have been monetized. One of the things, if you're using Zoom for free, you have given Zoom, and one of the things they're doing is monetizing your voice and your identity as well as who you talk to.
Okay.
So never, ever, 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 ever discuss anything that you wouldn't discuss in open public on Zoom. And never, ever, ever think of any of the things like your fingers, your face, your voice as being secret anymore, because if you've used Zoom, they've monetized it.
Well, one of the things that I've often done is I've often, I might say to someone, oh, can I borrow your, like they might be driving or something, and I'll say, oh, can I borrow your phone for something? And they'll go, sure, right? And then I'll open it up, and what I'll do is I'll just point the phone at their face, and it'll immediately unlock their phone because they've got the facial recognition. And like it is very easy to just unlock someone's phone by pointing it at their face. And so facial recognition is not the best
methods to handle the case if you're being required to authenticate and you don't want to authenticate. So a good system would have a way that you could authenticate by being compelled, and the result is not what they want. So imagine having a duress face that unlocks it to a different set of things that look legitimate but doesn't have the information they're looking for.
Okay.
It is an example of something you can do to help that. And so you say, well, what could I do that would subtly make it where I have to do something that have a legitimate information? Again, your face is not a password. Your face is part of your name, your identity of who you are. So you want to have a combination of things that would be, better. So an example might be to have facial recognition, a voice of please unlock, and maybe even a code I type in or do something. There are things like that could be done that you could improve those systems. Of course, it also depends upon what it is you want to protect. If you're merely protecting your Instagram account, maybe that's not so valuable as protecting the nuclear arsenal of your country.
Yeah.
And you use different things for different, so it's not the case of one security system fits all. You have different levels of security.
It's like how didn't someone manage to get into Donald Trump's Twitter account or something?
Yeah, they guessed. They guessed. I think it was MAGA 2020 exclamation point.
Yeah. So
I think it's something on that Twitter was something or other that person did, and I don't want to talk about the policy of it, but that was a social engineering attack. Now, MAGA 2020 exclamation point is something which is a trivial compute. There are programs that you can run on your PC, for example, that could crack that password in a fairly short amount of time. So you need to do something more than simply that sort of thing to protect it. But I guess the best thing to do is to make sure that if you are attacked, you at least know the attack. If you can't even know you're attacked, at least be able to mitigate the result if you've been successfully attacked. And one of the ways is to use different methods of authentication for different things. So if you are somebody that uses Microsoft, Bing, or Facebook, and their authentication gets stolen, you don't want that to turn into your loss of everything else. So these systems where Facebook or Google says, give us your thing and let us unlock stuff for you. It's like, well, no, have different methods of authentication, and then manage those things is a much better thing. But again, it's called defense in depth.
Yeah.
That you can't prevent, try to mitigate. That you can prevent, at least be able to detect.
Yeah.
And a password guess can be done offline, and you don't even know you've been had or even know you've been attacked until after it's too late.
One thing that I want to go into is I remember you saying about some of the gripes that you have with a particular programming language called Python.
Oh, well, and gripes is sort of thing. I mean, I'm disappointed in Python. I think Python does a number of things that are right, but I'm disappointed in Python in a number of ways. Now, I'm sorry because I know there's a Python cult out there. If you say bad things about Python or the design flaws of Python or the mistakes that the creator Python made, you somehow are a bad person. So I'd rather say that Python is not my favorite language, but no language is my favorite language. They're use different languages for different things.
Yeah.
And so the best thing to do is to have a good variety of tools for which you can select the better tool for the right task. And Python is good for some things, and it's not as good as for others. I will say that I think that there was some real unfortunate things that were made regarding Python, and there are some really good essays out there about why Python is not my favorite language. And so let's say that way that Python's not my favorite language for a number of reasons, but Python is a good tool for a number of things.
Like I do like Python as an introductory language because, I mean, if you're going to learn something like Java, it's been quite a while since I've used Java, but I'm pretty sure to just print something to the screen, it's system.out.println, right? And that confuses anybody that's new to programming as to what's going on. Whereas just having...
I think... And so if you had a choice often between, let's say, Java and Python, and you say, I could do it in Java and do it in Python, almost always your answer is probably Python.
Nah.
And so now the thing about you do with a language is you should look at it from a point of view of its philosophy, what it does well, what it doesn't do well, and also look at its robustness and its resiliency to stuff. And all those languages have their flaws. Just use them in the appropriate spot. So if you talk about introduction to computing, there's some really nice Python-based, IDEs that can get people starting to think about programming. But here, I think, is a big important lesson, is that it is extremely important to be multilingual.
Yeah.
Starting Deutsch and English, right? Speak Python and C and a shell and pick your language. Being multilingual makes you a better person, because the problem with knowing one language is you think the rest of you can get a situation where you think the entire world is that way. And your first language can also affect you quite predominantly as you see other languages. So you might sit there and say you see Python, and then you're experienced to a Go environment. You say, well, Go is not Python. I don't like it. It's da-da-da. And you say, well, but on the other hand, if your first language was Go, then you say, Python's not Go, and I don't like it, da-da-da, right? Once you see multiple languages, very diverse languages, then you get to see the underlying structure and how to express things. So having a language like Lisp, having a language like a Fortran, having a language like C, having a language like Java or Python, having a language like Prolog, have a language like Simula. These are very different classes of languages that give you insights into how to take a algorithm or concept and put it into execution. So Lisp and Prolog, for example, are very, very, very different languages that have very powerful things. They do some things well and other things that are kind of cumbersome.
Yeah.
Lisp allows lots of intricate, silly parentheses, right? is this thing there for stuff. But Lisp is extraordinarily powerful in what it does. Prolog, an inference language, is something that can be done some amazing things that procedural languages can't do. Perl is another language, I would say. If you're going to learn Python, then you should also learn Perl, because what Python, probably the biggest problem with Python is the Python community and the notion of there's one way to do it. That's an unfortunate thing, I think, in Python is there's one way to do it. This is the best way. It's a Pythonic way. And that, I think, is very poor thinking, as well as a poor way to think, as well as a very limiting set. So, and I remember, as example, of an introductory course of Python was given in class, and I was exposed to Python. And the instructor was trying to show you how you can develop Python and use the idle to go and tying loops and show you how you do something efficiently. And it turned out that the algorithm we're using was very inefficient. And all this stuff they were doing was showing all these Python tricks. I used a smarter algorithm, solved it in nearly constant time, and was done, right? Because I think like, we'll compute this big thing and use Python iteration thingies and so forth and on. Whereas all of a sudden you just look at the thing in a different way, and I understood the mathematics behind it and came up with a solution that was nearly constant time, typed it in on a string, press return, and for the next hours waiting for the instructor to go through all these other iterations of stuff. They never got to the algorithm it did. And so the Pythonic way is often, particularly when you're pushing the bounds of computation, is often not what you want to do. And when you're pushing the extreme computing, the Pythonic way is probably not the best way. It might be an okay way, it might be an efficient to express way, but probably almost certainly not the best way. And so Perl does the opposite extreme. Perl is there's more than one way to do it. So if you're going to learn object-oriented programming, start with Perl, because Perl doesn't force you to do it one way. Now the danger with Perl is they give you more than enough rope to hang yourself. And if you're not a good coder, you're not careful and methodical, if you're not well documenting, you can paint yourself into an oblivion corner, right? So Perl has its problems too. But the Python notion that you have an algorithm, you have a method which is better than what I can do is, I think, arrogant and limiting. You should have a language more like Go or C or something where you can explore those algorithms and produce something that can be efficient, that the tool rests for a task, as opposed to assuming that Python knows how to do it.
One of the things
my problems with Python often are with the community around it.
Well, I have my own gripes with the language itself, like the white space is one thing that you brought up, how white space is a part of the language. Yeah. That's one of my gripes with it. Another gripe that I have with it is that you can't... So in languages, in quite a few languages, you can just type ++ to increment a variable, or an integer, should I say. Whereas in Python, you can't go ++. That's just not something you can...
Yeah, that the syntax of Python, I think, is ugly. And back in the days when Fortran was on punch cards and column 6 meant something and white space was significant, you might have been get away with a syntactic of Python. But Python syntactically is an embarrassment. And the person who created Python did a really poor job of syntax. Now, it does what it does. From a teaching point of view, from an instructor point of view, it has a lot of things to say. But I would say to the Python creator, white space is not some non-renewable resource you have to preserve. White space should be syntactic sugar to help shape the expression, right? Now, people say, hey, aren't you the founder of the International Obfuscated Seed Code Contest? Blah, blah. Yeah. And that's a case where we're using irony and sarcasm to show you that merely a program that works is not good enough. It is not sufficient your program works. It should work well, it should be maintainable, should be well understood, and should be modifiable to improve things. The obfuscated seed code contest winners are often tangled, extraordinary levels of logical something, brilliant things, which are often completely unmaintainable and very, very, very difficult to fix or correct or change.
I mean, you can always go int b equals 89, int flug equals 90. I want it to look like that. If B equals Flug console dot console dot write line.
I don't hate Python. That's not a thing. I don't want to say that. Python does some things well, but I think the two biggest flaws of Python are its community, the Pythonic way, and the syntactical choices of the creator of Python did that I think are unfortunate.
But I just want to make sure this is fine here, right? This is fine fine programming. Sometimes I will do things.
But I would say what's not fine is what and why. So the comments of one of the things that Python does very well is tries to implore you to document and have the document, the Python doc stuff, I think is excellent. I even though I'm judge the SQL contest stuff, you look at my actual code, I try to make it as literate as possible. And when I have to do something very clever, I try to first write it in a way that seems obvious and then transform it into a way that's need to be and explain in my documentation why I didn't do the simple thing, why I did this other thing, right? And that's part of literate programs. So when I write Hello World programs, most of it is comments.
Fair enough.
And so on the code that I actually maintain, that's 20 years ago, I can go back into the middle of a file, point to a spot, and begin to tell you what's going on there and why it's there. Because the code is written in a way, and documentation is written in a way, and it's laid out in a way which is responsible and understandable and explainable to try to understand what it is you need to do. So when some program comes up and there's some problem, environment changes or the limit stuff, I have a chance to go back and understand it, even though it's maybe decades old.
Yeah. So
literate programming is very, very important. And I think Python does a really good job of that in trying to do all the doc stuff ahead of time, assuming you take advantage of it.
One person says, one person in chat real quick says, I've been working with COBOL for so long, I really miss the convenience of using an IDE.
Yeah, by the way, I program in COBOL too, so it is still a used language for a reason.
Yeah, one of the I do have to say one of the things that I like about one of the things I dislike about programming languages like C# and C++ and Java is their insistence. Now I know this is a mild inconvenience, but their insistence on using semicolons at the end of everything, right? At the end of every statement. Now, sometimes I'd like being able to be lazy with my semicolons. That's just me, and so I will give props to Python for allowing me to just not bother about semicolons at the end of certain statements.
The problem is, it's like saying if you've written languages, the reason why periods, for example, that kind of syntax stuff, having an end of a sentence is quite useful. Those sort of punctuation is actually quite useful if it's used to punctuate. So that's really how you do it is a language choice. But having punctuation allows you to take an expression and put a lot more meaning and nuance into it. Why we have commas and pauses in sentences and semicolons and colons and quotes and parentheses and so forth. Those in written languages have the same thing with programming as well. So those are nice stuff to show your punctuation helps in reading.
Yeah.
Especially if it gets to the point of your expressions become Germanic-sized, run-on, multiple compound, complex sentences with action verbs somewhere towards the end, right? Those are things that can be quite beautiful linguistically, but they may obfuscate rather than aid in understanding. Especially again, if what you're doing is scientific, where you're supposed to show your work and have people understand what you've done and benefit from what you've done and do better than what you've done. That's the value of doing something in science, is that your result is merely a stepping stone that, if explained and published well, allows someone else to do something even better. That's why answers are just temporary stuff to ask more questions about how can do this something even better. So my production code is very boring. And particularly if I have code which is involved in a scientific result or computational result, it is extraordinarily full of comments, right? It is, and it's not common for some real computational complex piece of code to have it be maybe 90% comments. If I'm doing some really complex algorithms that need to be explained to myself if I need to go back and fix them later, or to someone else who's benefiting from the result. Open source is good if the source is actually literate and can be used by someone else to do something even better.
The person in chat said to me, if you didn't have periods on COBOL, you'd be cursing out the person that wrote the nested if statements because you don't know where it starts and where it ends.
Yeah. And those pick 99.9 stuff and so forth. That's also identity division and data division stuff. That's sort of, those are things there. But again, COBOL had its use, particularly in early compilers. It was actually a very good compiler, and it's one of the reasons why it was so prominent used in language, in the language of business, for example. So it had a number of things going on. It has some, but anyway, languages have their really great points, and languages have their brain damages. Right? English has some great stuff, but it also has some extraordinary brain damage involved in the English language.
Like I like French, right? French is a really nice language, but one of the things that's really annoying is how everything is gendered.
And German's the same thing. Right? And so some extent, where gender, where you have nouns that have colored properties, like arbitrary masculine, feminine, neuter, or whatever your other hues that you have on an object. If those things convey information, they can improve it. So to say I have a beautiful red ball, I'm enhancing what ball is. Those modifiers are useful. But if I sit there and say I have a ball whose hash is 17 and whose 3D space coordinates end in the number 5, you go, huh? How did that help me understand what ball was? Well, more different than, say, is it der ball, d ball, or das equivalent of ball, right? Is it masculine, feminine, neuter, right? Those things often are arbitrary and capricious. So in the case of here's the problem, of course, is that there's beauty in some of that subtlety stuff, because French language has a lot of beauty and structure, and the people who speak and write the French language well are masters of an art form. But that comes at a price, just like in German, right? Has some really great things, but to try to figure out the gender of a table, right? Or the gender in the French of a calculator versus a computer, right? And stuff is that, but again, it doesn't convey necessarily information. It's a way of getting it wrong. It's right? Identifying a non-native speaker who doesn't know la calculateur versus a calculatrice, right? Those are things that can distinguish you. Say you don't know, you're not an inside club. Same thing with languages, right? At least in languages of computer variety, I should say, some of the stuff can get you in modifying of something improperly can get you wrong answers. But again, someone sits there and say, I've got a value. Why do I care with an integer or a float or something or other? I mean, and the answer is sometimes you probably do. It's one of the reasons why COBOL does a lot of stuff in the binary coded decimal, because it's often deal with commerce of objects or currency that it does better than
one of the things that I don't like about Python, and I like about one of the things that I actually don't like about GML is the fact that if I want, I like integer division, right? I like being able to take an integer, something that's most definitely an integer, divide it by something, and then the extra information that would be after the decimal point is just lost to the void of the computing realm. And I like being able to do that. It's a little bit annoying when to be able to do that I've got to go round or floor every time I want to do that. And so that's one of the things I do like about, that is why C# is one of my favorite languages, is because I can basically say, okay, this is an integer. It's not going to be anything else. It will always be an integer. And if I want to, I can also say, well, actually, I want it to be a long. I want a bit more information. And so, I can define things to be a long rather than an integer. That way I know. And if something is long, then I know that when it gets to 2 point something billion, it's not going to tick over back into the negatives. And I like...
So I want to reference, of those sorts of things, those kind of algorithm stuff. I put a link in there of a book called Hacker's Delight, which came from the Artificial Intelligence Memo number 239 by people like, great people like Gosper and Draconae and so forth. And it's a collection of really interesting algorithms using objects like ints and so forth to compute some amazing things. So if you want to do something like reverse a string with a bunch of integer operations, math operations, it'll show you how to do those sorts of things. It's so Hacker's Delight. You can look it up in Wikipedia. It's Addison Wesley book. You can also look up Artificial Intelligence Memo number 239 at MIT. And that has some really interesting algorithms of people that are very, very clever at using objects like integers and floats to do things. The International Obfuscated Synchron Contest had a really spectacular program. One of my favorites. It computed the MD5 hash. If you know about the MD5 hash, where it does a bunch of shifts and rotates and XORs and so forth. And this program computes the MD5 hash using entirely floating point numbers. And it has in this algorithm doing things like, it was like calling trigonometric functions and square roots and other things like that. But it actually correctly produces the MD5 hash, something binary, and it uses some very, 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 very clever Hacker's Delight type algorithms for how to do something like a bit rotate or a XOR numerically rather than, so it's a single expression, right, that produces the MD5 hash, but it does in a way using entirely floating point operations and floating point functions. That is quite a delight. Someone mentioned Grace Hopper. She was an amazing person. I had a chance to meet her once. Extraordinary in her brilliance. A lady who was way ahead of her time, and done a number of things besides COBOL that I think we really like.
Yeah, I do like one of the comments. Bill Baggins said, "I get the feeling that Python is a bit constrictive."
Yeah, I think so. I think the Python community, where there's a Pythonic way to do things, gets to be a little bit constrictive. And the result is that if the Pythonic way is not algorithmically efficient, you've got to break Python or avoid it.
I
Another thing, of course, is Python's not secure. I mean, one of the things, if you're really a system cracker, or if you're in a hacker, figure out how you can use Python to corrupt itself.
Yeah.
The same thing I do with Java, by the way. Right? If someone's coming, we used to be when I was would interview people, and the issue was someone says they're a Java person. I would ask Java, how could you in Java build a pointer to an object and smash an arbitrary location in memory using Java, right? And if you really understand Java, you know reason why Java has never been proven secure. The Java virtual machine is not proven secure, right? And so if you really know Java, here's a challenge. If you think you know Java, write a program in Java that allows you to arbitrarily modify bytes in arbitrary locations in memory.
Okay.
Right? Because that's one of the things that Java people say is, oh, well, it's all constrained and heaped and protected and da da da. Like, no, it's not. It does a good job, but if you are clever, and I thought, the part of the thing is in looking at evaluating the safety of Python, is one's ability to take a Python program and have it corrupt itself.
Yeah.
Right? Where Python has vulnerabilities, you can do things to Python to cause it to do unfortunate things. I don't say that's unique to Python. It's just that some people say, well, Python is secure. Well, no, it's no more secure than any other language.
Well,
Python's good for a number of things. Use Python for things it's good for, and don't use it for things that aren't good for. And
I do want to say
multilingual and no more than one language.
I do want to say about the Python being a bit constrictive comment is I think a boa constrictor might be a bit more constrictive than Python, honestly.
Yes. But again, it's a good thing. So languages, there's a number of class of languages that are there. If you at least know elements, you've worked in elements of different languages over the years, then you can pick the right tool for the right job, rather than say everything is a nail because I don't know how to use a hammer. Right? That's you don't want to be in that situation. You want to be in a case where I have a tool to use. And so for example, I wrote a language called Calc, C-A-L-C, and then Calc is a multi-precision interpreter. It's a C-like language, and Calc is what I use to compute pi to 100,000 digits. Now it's computed to 1 million digits, and it's happening written in C. But what Calc does is Calc, and I'll point you at the GitHub repository. There's a GitHub repository. Calc does calculations in rational numbers. So one thing that Calc can do very well is express the value 1/3. Exactly, right? And in Calc, if you add 1/3 plus 1/3 plus 1/3, you will get exactly 1. Not rounding error 1, you'll get exactly 1. Calc actually uses also to understand complex numbers, so we can do a over b plus c over d times the square root of 1. So we can do complex values as well. And so when we calculate something like the arc hyperbolic cotangent of 37 times the square root of -1, we do it all in rational arithmetic, bounded by stuff. When we calculate pi, we do it in rational arithmetic, those expressions, and just do it to the point where the precision is known. So Calc is a language that's used for exploring algorithms and not being limited by numeric precision of your system. So it's arbitrary. You do arbitrary large numbers. You're only limited by the memory and the patience you have on your processor speed.
Yeah.
So it's open source and code is there, and you can look at stuff and enjoy things. It's a, I guess for the main thing, I guess this is the main. We talk about the main URL is here. We can put that out. You can put that on there. So yeah, that's I think it probably is the main language page, and there is a you go back. There's the main website here is here, right? And so calc's pretty efficient. Now you can do better than calc, but calc can give you pretty good efficient stuff for handling things like exploring how a series converges, or calculating pi to 100 million, or 100,000 decimal places, something like that. You can do that in a relatively easy way.
I do.
But again, it's a C-like language. It's not exactly like C, but it's an object-oriented language stuff. You can do weird things, but it's meant to explore algorithms.
I see. What I did want to say is, because we should start ending up, but I put out a poll today asking people what is the best kind of pie, and there were 4 options. There was apple, 3.14, mince, and cottage. Right? 3.14 got 48% of the vote. Then apple got 31% of the vote. Then mince got 10% of the vote, and cottage got 12% of the vote.
For apple rather than 3.14 because 3.14 is such a limited approximation where apple pie is what it is, unless it's baked poorly, in which case it's what it is, but you don't like it, right? So in that sense, but pi as a symbol is quite useful for stuff. By the way, on the on the history of pi, it wasn't until the 1700s that someone decided to take that value and use the Greek letter pi. I believe it was like 1700 something or other, if I remember correctly. That the name pi, certainly the adoption of the symbol of pi came about, I believe, if I recall correctly, like 1706 or something or other is where we start to see people using this Greek symbol pi for that. But there are other things. There's some uses of the word pi, of the symbol pi in the mid 1600s, but concept of the value, the ratio of the circumference to the diameter, goes back millennia, but the use of the symbol pi came about.
I am.
By the way, Euler originally used pi to be 2 pi. He liked to use tau, what we call tau, but never. And so his early essays on stuff, Euler was using pi as the value of 2 pi.
I do want to say that there is one pie that I forgot to add, and that was terracotta pie. If anyone knows that reference, I don't know if anyone knows that.
And of course, there's also humble pie. So I no doubt I made some errors in my statements here that people will point out. No doubt, and people correct that. So I will have humble pie and say sorry for the errors. The opinions, again, I hope I haven't offended Python people, because I hope I gave you a balanced perspective. But there's lots of other things for pi. I would think that if you go to Wikipedia and look up pi, there's a really nice article that, again, PI, you type in PI, search for Wikipedia on just pi, which is also the history of pi. You'll get a nice history of pi. You'll get some nice stuff talking about its use, the series, the adoption of the symbol, modern computation. You get to do giants of people like von Neumann, Gosper, so forth, and some other fun things that you might not have known about pi. It doesn't get to be too mathy, but it has some nice pictures on it. So give that a function.
But yeah. Anyway, we'll end up the stream here. I think that it was a nice thing to just bring, because I did do this poll 3 hours ago, so it was probably about half an hour before the stream, and I just wanted to see what people's answers would be. And as I said, like there's some answers that I didn't put in because I didn't think about them. Like having something like terracotta pie would have been like a funny little answer. Or I saw like a lot of people in the comments were saying cherry pie. You had cherry pie, you had cream pie, and rhubarb pie. So
veggie pot pie. I mean, Aussie pies are pretty awesome pies as far as pies go.
And people were asking, what is cottage pie? And yeah. Oh, I know.
But yeah, if you go to Australia and you ask for a meat pie or a veggie pie or a fish pie, they have some really awesome stuff in there as well. So it's pie is a lot of cultural stuff there. So
here in New Zealand, I believe over in America, a lot of people have sweet pies, where it's like apple pie, rhubarb pie, cherry pie, and all that. Whereas over in New Zealand, if you ask for if I go over to America, I'm likely to get a sweet pie or a dessert pie. Whereas if you go over to New Zealand, if you ask for a pie, you're likely to get a savory pie rather than anything sweet.
And that's the biggest thing that people who don't know about that set, having a pie is basically a nice way of containing some goodness. That goodness could be meat, veggie only, fish, veggie stuff, surrounded by a wonderful dough that's been baked in a nice, containable sort of thing.
Yeah.
So yes.
Yeah. But with that, I will end up the stream. Thank you very much, Landon, for coming on. It was very nice to talk to you about all this.
Reminisce with stuff and to take it in various ways. We'll have to do this again sometime. I would say keep asking questions because questions are more valuable than answers. Know lots of different languages so you can use the best tool for the best thing. Don't think that one solution fits all. And keep enjoying our favorite universe. Yeah. And by the way, I do have a channel I'm going to be going on about our favorite universe, but for now, just say I hope you keep enjoying our favorite universe because there's lots of good things in here to enjoy. Yeah.
And with that, I will see you in the next. Oh, yeah, wrong thing. I'll see you in the next stream or the next video. Between you and me,
like and subscribe, thumbs up on this channel. Help him get to 100,000 so he can do the 100,000 digits of pie show.
Yeah. Yep. But anyway, I'll see you in the next stream or video. Thank you. Oh wait, no. And between you and me, thank you for watching.